AI's rise looks unstoppable. But wait, it isn't what it seems. Twice the entire field flatlined. First in the 1970s, when a scathing government report gutted its funding overnight, and again in the early 1990s, when the industry's biggest bet collapsed and took the money with it. Labs shut down. The smartest researchers alive were convinced it was finished for good, and therefore, so was AI. Except twice, they were wrong. Nobody watching this knows that yet. AI didn't have one origin story, it had two funerals. So how did we actually get here? The real answer starts nearly a century ago, with a British mathematician and a question almost nobody at the time took seriously. Can a machine think? That mathematician was Alan Turing, and by 1950 he'd already spent the previous decade helping crack Nazi Germany's Enigma code, work that historians now credit with shortening the Second World War by years. After the war, Turing turned his attention to a stranger problem. He published a paper that didn't try to answer whether machines could think, because he thought the question itself was hopelessly vague, almost impossible to define cleanly. Instead, he proposed a test. If a human judge, having a text conversation with both a person and a machine, couldn't reliably tell which was which, the machine could be treated as exhibiting intelligent behavior. It became known as the Turing test, and for decades it was less a scientific benchmark than a distant target nobody expected to hit anytime soon. Turing predicted it would take until around the year 2000 before a machine could fool judges convincingly, and he wasn't far off. The field got its actual name 6 years later, in the summer of 1956, at a workshop at Dartmouth College in New Hampshire. A young mathematician named John McCarthy, along with Marvin Minsky, Nathaniel Rochester, and Claude Shannon, gathered a small group of researchers for what they called the Dartmouth Summer Research Project on Artificial Intelligence. It was McCarthy who coined the term itself, choosing it specifically because it sounded distinct from existing fields like cybernetics and automata theory. Their founding proposal made a claim that still sounds audacious today: that every aspect of learning or intelligence could, in principle, be described precisely enough for a machine to simulate it. Nobody in that room thought this would take more than a couple of decades. Early results seemed to justify the optimism. Researchers built programs that could prove geometry theorems, solve algebra word problems, and play checkers well enough to beat their own creators. In 1958, psychologist Frank Rosenblatt built the Perceptron, a simple artificial neural network loosely modeled on how neurons connect in the brain, funded by the US Navy. Newspapers at the time described it as a machine the Navy expected to eventually walk, talk, see, write, reproduce itself, and be conscious of its own existence. In reality, it could distinguish very basic visual patterns, little more than telling a square from a triangle under controlled conditions. The gap between promise and reality was already enormous. Then came the first funeral. In 1969, Marvin Minsky and Seymour Papert published a detailed mathematical critique titled simply Perceptrons, showing that simple neural networks like Rosenblatt's had fundamental limitations, unable to solve certain basic logical problems, no matter how they were trained or how much data they were given. The book landed like a verdict. Funding agencies took notice almost immediately. In 1973, a scathing government-commissioned report in Britain, known as the Lighthill Report, concluded that AI research had failed to deliver on its grand promises and recommended cutting most public funding for the field. Across the Atlantic, DARPA quietly redirected its own AI funding toward narrower, more immediately practical projects. Funding collapsed on both sides of the ocean almost overnight. Historians now call this period the first AI winter, a years-long freeze where artificial intelligence became almost a dirty phrase in serious computer science circles. Researchers quietly rebranded their work under safer names like informatics or machine learning just to keep it funded, and entire labs shut their doors. The field thawed briefly in the early 1980s with the rise of expert systems, programs designed to encode the specific knowledge of human specialists, doctors, chemists, geologists into long chains of if-then rules. Companies bet enormous money on the approach, and by the mid-1980s, the expert systems industry was worth well over $1 billion annually. Then the systems proved brittle, expensive to build and maintain, and completely unable to handle situations their rules hadn't specifically anticipated. By the early 1990s, that entire bet collapsed, and it took the funding down with it almost as fast as it had arrived. A second AI winter set in, arguably colder and longer than the first. Twice now, the smartest people in the field had walked away convinced it was over for good. Both times they were wrong. Progress didn't stop, It just moved underground into narrower, more measurable problems where success could be proven with a scoreboard instead of a promise. In 1997, IBM's Deep Blue defeated reigning world chess champion Garry Kasparov in a 6-game match, the first time a computer had beaten a sitting world champion under standard tournament time controls. It was a genuine milestone, and it made global headlines, but it was also a narrow one. Deep Blue couldn't do anything except play chess. It didn't understand what a chessboard was, what a game was, or what winning even meant. It simply searched through hundreds of millions of possible move sequences per second faster than any human brain ever could, guided by rules programmed directly by its engineers. The real turning point, the one that quietly built the foundation for everything happening today, arrived in 2012. A neural network called AlexNet, built by graduate student Alex Krzyzewski along with Ilya Sutskever and their advisor Geoffrey Hinton at the University of Toronto, entered the ImageNet competition, an annual contest to correctly identify objects across more than 1 million labeled photographs. AlexNet didn't just win, it beat the next best result by a margin nobody had seen before, cutting the error rate by almost 11 percentage points in a single year, a leap that normally would have taken the field the better part of a decade. The technique it relied on, deep learning, training many layered neural networks on massive datasets using powerful graphics processors originally built for video games, had existed in theory since the 1980s. AlexNet proved it actually worked at scale, and the entire field pivoted almost overnight. Within a couple of years, nearly every major tech company had quietly become a deep learning company. The next 4 years were a sprint. In 2016, DeepMind's AlphaGo defeated Lisadol, one of the world's top Go players, 4 games to 1 in a match long considered far too complex and intuitive for any computer to master. Go has more possible board positions than there are atoms in the observable universe, so brute force searching, the trick that had worked for chess, was completely useless here. AlphaGo instead learned patterns and strategy the way a human might, through millions of practice games against itself, compressed into a training process that would have taken a human many lifetimes to replicate. Then in 2017, a team of researchers at Google published a paper with a strikingly casual title, "Attention is all you need." It introduced something called the transformer architecture, a new way for neural networks to process language by weighing the relationships between every word in a sentence simultaneously rather than one word at a time in sequence. It sounds like a small technical adjustment. It wasn't. Transformers could be trained in parallel across enormous amounts of hardware, in a way older architectures simply couldn't, which meant they could scale up in size far faster than anything that came before them. Nearly every major AI language system built since, including the one that helped generate the visuals for this very video, is a direct descendant of that one paper. For a few years, transformers quietly scaled up inside research labs, mostly unnoticed by the public, growing from millions of parameters to billions, then hundreds of billions. Then, in November 2022, OpenAI released a chat interface built on top of one of these models and called it ChatGPT. It hit 1 million users in 5 days, a growth curve unlike almost anything the tech industry had ever seen for a brand new consumer product. 70 years of theory, 2 AI winters, and one obscure 2017 research paper collided into a single product that ordinary people could suddenly just talk to. None of this happened because someone finally cracked the secret of consciousness, or built a digital brain from scratch in a lab. It happened because ideas that had existed since the 1950s, neural networks, pattern learning, statistical prediction, finally met enough data and enough raw computing power to actually function at the scale those early researchers had only imagined. The dream from that Dartmouth workshop in 1956 didn't get realized by one genius breakthrough decades later. It got realized by decades of failure, 2 funerals nobody expected the field to recover from, and one architecture change in 2017 that happened to unlock everything at once. So the next time a chatbot answers you in half a second, it's worth remembering what's actually sitting behind that reply. 70 years of dead ends, 2 winters that nearly killed the entire field for good, and a small number of researchers who kept working on it anyway, quietly, often without funding or credit, long after almost everyone else had stopped believing it would ever go anywhere.